Okay, so let's talk about this thing, infinity, and how it comes into play with limits. So there's two ways, sorry, this is just such a bad infinity. There's two ways that you might come across this when working with limits. The first way we're going to look at is what's happening to our limit as x approaches a positive or negative infinity. Now, we've done this graphically plenty of times, where we've looked at a graph and going to negative infinity, we go to the left and see what it approaches, and going to positive infinity, we go to the right and see what it approaches. And usually what this is determined by is the presence or lack thereof of some type of horizontal asymptote that the function may have. Now that's all great until we're no longer looking at a graph. So basically this is going to be a look at how to deal with this whenever you're doing limits algebraically. Example 1. Given that f of x equals 3x squared plus 1 over 5x cubed plus 2x, find the limit as x approaches infinity of f of x and also the limit as x approaches negative infinity of f of x. Okay, so let's do the limit as x approaches positive infinity first. Okay, and so what you're basically going to do whenever you're doing these problems where x is approaching infinity, it's a little complicated because we cannot, and I repeat, do not just plug in infinity, okay? We can't substitute it in. That would be very convenient, but this will make Miss Wright very upset. And the reason being, infinity is not a number. It's a concept. You can't plug a concept into a function. So this is where your experience with horizontal asymptotes and understanding the end behavior model is going to come into play. So if you don't remember that, the basic concept is which one wins. Now let me clarify. By one, I mean the numerator or the denominator. And by wins, I mean which one grows faster. So let's think about this. On the top I have 3x squared plus 1. And I'm going to substitute in a very, very, very large number, and it's just going to keep growing and growing and growing. So when I have 3 times a massive number like a billion, trillion, quadrillion, which isn't real, but you get my drift, squared, and then I have this little dinky plus 1 on the end, he's not really going to be very impactful. So he's kind of not what I'm going to focus on. Instead, I'm going to focus on that 3x squared in the numerator. And then the same is kind of true for the denominator, where if I have this 5x cubed and we're going towards infinity, it's going to get massive. Whereas this little tiny 2x, he's going to become less and less relevant the larger infinity gets, leaving me with this 5x cubed. So this is what the end behavior model asks us to do, to look for the highest degree in the numerator or the denominator to kind of get an idea of what the graph is going to converge to as we go further and further out. So when you're doing these problems, what you'll see me often do in my answer keys is simply circle that most dominant part of the numerator and of the denominator. And that then allows me to answer this question over here, which is out of those two things, those two terms, 3x squared and 5x cubed, which one is growing faster? And in this case, the 5x cubed is going to create a number that, even though we're thinking in terms of infinity, really large numbers, okay, the x cubed is going to create a number that's even bigger than the 3 times a really large number squared. And as we continue to infinity, this guy just gets bigger and bigger and bigger and bigger and bigger and bigger, which means since he's in the denominator, our actual overall value is getting smaller. And in fact, it will actually approach a value of 0. So again, when you have a big number over something that's just going to get bigger and bigger than that numerator, it's going to just approach 0 every time. Okay, so now we're going to do it as we go to negative infinity. And this time we're going to go a lot faster because now we know what we're looking for. We're going to have a 3x squared as our dominant part of the numerator, 5x cubed in the denominator. Again, cube wins over squared. Okay, so it's going to do the same thing. that denominator is going to get really, really, really big, much bigger than the big, big number in the numerator. And because of that, the overall limit is going to be approaching 0. In this case, the fact that it's positive infinity versus negative infinity doesn't make a difference, since 0 doesn't really have anything to do in the end with positive and negative. On to example 2. Given the function f of x equals 3x squared plus 1 over x plus 5, find the limit as, again, x approaches positive infinity and the limit as x approaches negative infinity of this function. So let's start with the positive infinity limit first. Actually, let's write the function here. And again, we're going to think that same question to ourselves out of the numerator and the denominator. To figure out which one wins, so to speak, we need to first figure out what that dominant term is for each one. So in the top, as we go to infinity, this little 1 is not going to be a big deal, but 3x squared will. And in the denominator, as we go to infinity, the plus 5, not relevant, but x will be. So we end up with 3x squared and x being our end-behavior model. Out of these, the one that is going to win or grow faster will actually be in the numerator this time, because it has an x squared, whereas the denominator is just an x to the power of 1. So this means we're thinking of a number getting really huge in the numerator, growing really fast, faster than the still very large number we're going to get in the denominator. So in this case, it's definitely not going to 0, because the numerator is larger than the denominator. And anytime this happens, we get something that is unbounded. Okay? So that means that we don't actually have a horizontal asymptote. These are the ones that have oblique or slant asymptotes instead. So there's going to be some sort of either positive or negative infinity that we will approach as we go to the left and right on the graph. So for these, I just think to myself, okay, if I'm thinking of a really large positive number, it's growing more and more positive. If I square that number, it's still going to be positive. And then the denominator, if I plug in a really large positive number into x, it's just going to stay positive. So in this case, this particular function will approach infinity as x approaches infinity. But do remember, that's a form of a non-existent limit in reality. We just like to clarify if it's positive or negative infinity to gather more information here. Okay, and that is because it's technically unbounded. Now let's look at the limit as x approaches negative infinity. So the same terms are going to be our end behavior model for both cases. So once you do it for the first one, the second one's easier in that regard. But this time, we're looking at a negative infinity. So we've got to be careful with those. They do sometimes make a difference to our answer. So again, this 2 is going to overpower the denominator, the squared. And so we know we're going to get some sort of unbounded answer. The question is it positive or negative infinity? So if we think about plugging in a really, really large negative number and squaring it, that's just going to make it positive. However, if we plug a really, really large number in for x, it's just going to stay a really, really large negative number. Okay, so that means we're going to have some sort of big, big, big positive divided by big negative, which means overall we'll be approaching a negative infinity as we go to the left on the graph. And again, same rules apply. Technically, that's not a limit because it is unbounded. Now for example 3. So given that f of x equals x squared minus 1 over 2x squared minus x minus 3, find all horizontal asymptotes. So this one has a different phrasing, but what you're going to do is actually the exact same thing. So anytime we're asked to find horizontal asymptotes of a function, we have to check what the limit approaches as x approaches infinity and negative infinity, because most of the time they match, but there are some cases where they don't, so you always have to check. So looking at that positive infinity first, as x approaches positive infinity of the function, figuring out our dominant terms in the numerator, it's going to be x squared, and the denominator is going to be a 2x squared. So in this case, there isn't really what I would call a winner, but there's a tie, right? They both have a power of 2, so no one is technically overpowering the other. They're the same. So this is that case where it's really the coefficients that end up being important to us. So in this case, we're squaring the really large numbers, so whether they're positive or negative, it's going to end up giving us a positive value, and it's just going to be the ratio of their coefficients. So for that one, it's 1/2. And again, for the negative infinity one, as x approaches negative infinity, again, they're both x squared, so even if I have a negative number, a really, really large negative number I'm approaching, once I square both of them, it's going to become positive. So it's still going to give me that same limit of 1/2. Now, you notice we got the same thing here. Not a big deal. That happens a lot. But you always have to check. Always. So our horizontal asymptotes, our final answer, is just one of them. And it's y equals 1/2. Okay, so for our final example, we're going to make things a little more complicated for you. So what if it's not just a regular polynomial on the numerator and the denominator? Because obviously there are a lot of functions where that won't be the case. And so one we come across a lot is a radical, some sort of square root function. They're actually not as bad as they look, but we do need to clarify a few things. A lot of people think we can just break apart radicals with the expressions inside of them. That is not the case. However, since we're using in-behavior models, we're still going to focus on only one part, the most dominant part of that expression. So what am I talking about? Well, just like in previous examples, if I'm approaching a massive, massive value, this little tiny +1 is not going to be the determining factor of what that's going to do to my overall function. So just like in the denominator, we don't really look at those constants or any term other than the highest power. So for this one, that 2x squared in the radical is the highest degree, and in the denominator, 3x is the highest degree. So I'm going to kind of explain what I'm doing a little bit more detailed in this one. So when you look at square root of 2x squared, you can break apart radicals with multiplication. So it's going to be the same thing as thinking of it this way. And the 3x is in the denominator. And if we're noticing, we have the square root of x squared right here. So that's simply going to look like a square root 2 times x over a 3x. So what this means is we really have that tie again between who wins, because both, when you actually look at what the function's doing, have about the same thing going on, a power of x in the numerator and the denominator. And in the previous example, we said this would simply leave us with that ratio of their coefficients, which is still true. The only thing you have to be careful with when you're dealing with square roots is the signs. Since we kind of simplified it here from what it originally was in, let's think about the positive negative stuff. So for this example, since we're looking at positive infinity, it's not super exciting, because if we squared positive something large and then took the square root, it would still be positive, and 3 times something really big and positive would still be positive. So for this one, we're just going to get a positive root 2 over 3 as our final limit. Now, if we're doing the same thing as x goes to, or approaches negative infinity, a really large negative number, we have to make sure that would still be the case. So I would still be doing this same process again, but I'm not going to make you rewrite it. So just think of a big negative number being squared and then the square root being taken. That's going to result in a positive. But 3 times a really big negative number is going to stay negative. So for this one, we actually get a negative root 2 over 3. So we have 2 different horizontal asymptotes.